Welcome back to week 11 of the problem solving session to Introduction to Fluid Mechanics course. And in this week, we will discuss about the final part of this course, that is the integral form of the momentum conservation, which basically means we will start discussing about the Navier-Stokes equation, and then we will discuss some exact solutions of the Navier-Stokes equations, namely the flow through flow between two infinitely large parallel plates and flow through pipe. So we'll discuss these two problems, and then we'll see how the solution are obtained for this special case of the Navier-Stokes equation, which are indeed the exact solutions. And then we'll see its implication on more relevant problems such as flow through pipes, which you can correlate that if we solve the Navier-Stokes equation for flow through a cylindrical pipe, it basically gives us the understanding of flow through all the type of pipes and ducts that we use in our day-to-day life or in industrial scenarios as well. So that's the main gist of the remaining two lectures, today's and the next session. So with that, I think we can start today's discussion. So as per our regular agenda, we'll briefly go through the concepts, and I think this week it's fairly more important than other week because it's very derivation heavy. So I think it would be indeed very important to go through the derivations of the Navier-Stokes equation very carefully and understand how the final form of the Navier-Stokes equation are obtained, what are its implications, and what are the inherent assumptions that are made to derive the Navier-Stokes equation. So this would be very important. So briefly go through them, and then let's see what we get. So if there's any doubt, you might ask me anytime during the discussion. So with that, I think we can start. So as I mentioned, we discussed the integral form of the momentum conservation. So basically, if you remember, we discussed our differential form, which was basically we obtained the governing equations using the Reynolds transport theorem. We'll carry forward that same understanding, but we'll try to obtain the momentum conservation equation. Of course, we already did in the previous discussions, but now we will try to impose some specialized cases or specialized scenarios by which we can simplify the momentum conservation equation, or I think the correct or appropriate word would be to make it more familiar, okay, with the terms that we already know, such as velocity and such as the velocity field. Okay, so let us see why it is important to make the Navier-Stokes equation a bit more familiar, so that the solving it becomes a bit more less cumbersome. Okay, so that's the motivation. So let's see. So this is the, as you can see, this is the linear momentum conservation equation obtained from the Reynolds transport theorem. I think it's quite straightforward. Now what we do is we try to impose two conditions, okay, two simplifying conditions or two major assumptions. That is, first is we consider a stationary reference frame. Okay, that's the first thing, because we already discussed in the previous session like what a moving reference frame, I won't say moving, but then accelerating reference frame results in, or what implications this accelerating reference frame has on the derivation of the conservation equations. So you already know it turns out to be much more complicated. Of course, there is a acceleration correction term in the left hand side of this equation which we have to deal with. So in a way to avoid that, we will try to directly impose that. We will consider that the frame of reference is stationary. Okay, that's the first assumption. Second is that our control volume is non-deformable. Okay, so these are two conditions that we will impose while deriving the equation. Let us see what implications does it have. So I think by now you already know that the implications of these two assumptions are straightforward. First is that if the control volume is stationary, Okay, then what happens is that the this relative velocity term in the flux term, in the momentum flux term, becomes equal to the absolute velocity of the fluid. Okay, so that's first implication for a stationary control volume. And second is that if our control volume is non-deformable, okay, what would happen is that this time derivative term can be taken inside the volume integral. Okay, those are the two implications that we have. Basically what happens is, if we do that, we will able to obtain the differential from the equation, okay, from the integral form. That's what our main objective or main idea is. Okay, so I think in the very first lecture, I think the very first lecture itself, or while we are discussing about the hydrostatics, we discussed that this force acting on the control volume, or I think I won't say the hydrostatic part, but I think in the earlier part of this course we discussed that the force acting on the control volume can be decomposed into two major parts, that is the surface forces and the body forces. Okay, I think by now you already know these definitions, so I won't go into it, but basically from the perspective of today's derivation, the surface force would basically be the pressure forces and the stress forces, or the stresses, and second, the body force is the gravity in this case. Okay, there can be other body forces such as magnetism and say electric field. Okay, but we will not consider those. We will just consider the gravity for the simplified scenario. Okay, but just want to let you know, it's not a generalized case. Okay, gravity is not only the body force, there can be other type of body force as well, and depending upon the work that you do in the later part of your academic life, say if you do a master's or PhD, the body force might change to say electromagnetic force or magnetic force. Okay, it might depend, it depends on the type of problem that you have in your hand. Okay, but for a basic fluid mechanics course, we will just keep it as the gravitational force. So for deducing the surface force, you know it quite well that we take the help of traction vector, the definition of which is shown here. So I will again not repeat it because we have discussed it very thoroughly in the very first lecture, and I think now we can directly know its implications. Okay, so basically we will do a dot product between the stress tensor and the normal vector, and the traction vector will give us the stress components along the direction of the normal vector. Okay, so that's what we do to find the traction vector. We do a dot product between the stress tensor and the normal vector. Okay, and as you can know, this will end up with as a surface integral because it because it gives us the surface forces. Okay, now for the body force is again a much more simpler analysis. We just consider this small bi to be the body force acting along the I direction per unit mass. Okay, so the volume integral over the control volume will give us rho times the volume integral over the control volume will give us the total body force acting along the ith direction. Okay, then similarly if you look back to this equation again, we'll try to do it, start discussing it with, for the first component, say along the ith component. Then the right hand side of the momentum conservation equation can be simplified to this form. Okay, so we just consider the ith velocity component. Okay, now what you see is that we have a volume integral and a surface integral. Similarly, we again have a volume integral and a surface integral on the left hand side. So now we cannot directly remove the integration because these are two different kind of integrations. One is a surface integral and one is a volume integral. So what we need to do is we need to convert either all of them to the surface integral or all of them to the volume integral. Okay, but now since we are doing a finite volume analysis, basically we are considering the entire force acting on the entire control volume. So it just makes sense that we treat these forces acting on the entire control volume and just consider this force, the integrals in terms of the control volume. Okay, that makes it more simplified and more generally acceptable. So with that idea, we know now what we'll do. We need to apply the Gauss divergence theorem to convert these surface integrals to volume integral. Okay, again, this is something that you already know. That's what I like about this later part of the course, because students are expected to know most of the basics, and this basic the later part of the course are basically the applications of the fundamentals. So I just like to teach the later part because I don't have to dig deep into each and everything. So yeah, that's good. I won't now say how it is obtained, so I will just directly say that we apply the Gauss divergence theorem to convert this surface integral to volume integrals. Apply the same now to both the sides, the left hand side and right hand side of the momentum conservation equation. Okay, just to again give you an idea or link between the topics that we discussed previously. Now you can understand that we are in the paradigm of fluid dynamics. Why? Because we are considering the forces that acts on the control volume, or that generates or actuates the fluid motion. Okay, so now you already know, like, these both the body forces and the surface forces are the sources of the fluid motion. They can actuate the or generate the fluid motion. That's why we are under the paradigm of fluid dynamics. Okay, again a simple takeaway, but a good way to link your previous understanding to the current discussion. Okay, so with that I think we can proceed further. So now you can see that all these terms, after applying the Gauss divergence theorem, all the terms in the equation now have a volume integral or a control volume, or elemental control volume. Now again, you know that if we consider an arbitrary control volume, arbitrary shaped control volume, for this integration to be satisfied, you need the integrand to be equal. Okay, or in other sense, like if you just take all these terms, say on the left hand side, and carry forward the volume integration, and then and of course the right hand side will become equal to 0. Now for the any arbitrary shaped control volume, for this integration to be 0, the integrand must be equal to 0. Basically now you will see that, let me just write it for your simplification, for your understanding. So if you take this to the right hand side, take this to the right hand side, so then you will have del dot tau I, volume integral of del dot tau I plus rho bi minus dou by dou t of rho ui minus del dot rho ui v dv to be equal to 0. Now for this integration to be equal to 0 for any arbitrary shaped control volume, you must have the integrand to be equal to 0. So this has to be equal to 0, and if this is equal to 0, you can get this form. Basically, if this is equal to 0, take these negative sign terms on the right hand side, you will end up with this form, which is the differential form of the momentum conservation. And this generalized form of the momentum conservation equation in terms of the shear stress components is also known as the Navier's equation. Okay, so I think it is already was emphasized by Professor Chakraborty in the lectures. So this is known as the Navier's equation, not the Navier-Stokes equation. We will see how the Navier-Stokes equation is now obtained. Or also this equation also again also known as the Cauchy momentum equation. Okay, so now I would like to take some time to discuss about the relevance or the large scale implication of this equation. Okay, so let me take some time just to discuss about it. First is that for any kind of fluid flow, okay, I would say for most, even for the advanced research level problems, okay, this equation, the Navier's equation, turns out to be the general governing equation for the fluid flow. Okay, not the Navier-Stokes equation. I will tell you why. See, when we apply Navier-Stokes equation, there are certain assumptions which we have to apply on this Navier's equation to obtain the final form of the Navier-Stokes equation. Okay, even though Navier-Stokes equation is the much celebrated equation that we usually say to be the cornerstone of the fluid mechanics community or fluid mechanics subject, which is indeed true, but it's not the most generalized form of the momentum conservation equation. Okay, the most generalized form is indeed the neighbors equation or the Cauchy momentum equation. So you can see that this equation is still in terms of the shear stresses. Okay, so the modifications on the shear stresses are made by considering some assumptions such as the Stokes hypothesis and the Newtonian fluid, which makes this neighbors equation or the Cauchy momentum equation the much celebrated Neighbors-Stokes equation. Okay, but there are some scenarios, there are some very critical fluids which do not fall under the umbrella of Newtonian fluids. A very popular example, and I think very important example, a very important example is human blood. As we discussed previously, this human blood is not a Newtonian fluid. Okay, it's a non-Newtonian fluid, and you cannot model the flow of blood using the Navier-Stokes equation, because in Navier-Stokes equation they inherently assume that or consider that the fluid is Newtonian. That's why any researcher or scientist who is working on the modeling of blood through human veins, again modeling human veins is again different mountain to climb, but just considering the fluid itself, that is blood itself, is not Newtonian. So to model the flow of blood, you indeed need to take the help of the Navier's equation or the Cauchy momentum equation. Okay, and you have to find the correct form of the relation between the shear stresses and the velocity components to model the blood flow. Okay, so that's the idea, and I think that's the motivation for anyone who is watching the video, to understand the importance of the Neighbors equation or the Cauchy momentum equation. Okay, now, and I think I already revealed the script for today's discussion by saying that we have to model the stress components in terms of the velocity components, and I will tell you again why we need to do it. Okay, so let us proceed further. I hope there is no doubt till now. If there's any doubt, I will give you a minute to ask. I will stop for a while. If there is any doubt, you can ask. Otherwise, we can proceed further. Okay. Just wanted to make the correction. It seemed that I made a mistake there. Okay, so if there is no doubt, let us proceed further. So as I was saying, the more generalized form is the Neighbors equation. Okay, so now as I already told you, a more convenient way to solve this equation would be to correlate the stress components in terms of the velocity components of the fluid. Now you may say, why we need to do it, right? You can we can just go ahead and solve for the stress components and then solve the equation, even though it's it is possible, but it's a possibility that you might think, but the thing is, it indeed turns out to be impossible to move ahead if you just know the stress components which are not correlated to the velocity components. Again, let us see why. So you can see that if, of course, the stress tensor turns out to be symmetric, so the number of unknown components in the stress tensor turns out to be 6. Okay, I'll leave it as an exercise why there are 6 independent components in the stress tensor. We already discussed it, but again, it would be a good practice for you to recapitulate or revisit the stress tensor. Okay, and you know it is symmetric. So since it's symmetric, it has rather than having 9 independent components, it has 6 components. Okay, fine. Then for velocities, because since the equation also has velocities in it, there are 3 velocity components, considering we are solving for a 3D velocity field. Okay, so in total, again, we are of course considering pressure to be embedded in the stress tensor, so we have total of 9 variables. But now the thing is, there are 9 independent variables to be found, and the number of equations that we have is only 4. How 4? Because it's a vector equation. The momentum equation is a vector equation, so there is 3 momentum conservation equation along the x, y and z direction, and the 4th equation is the mass last conservation equation. Okay, so you have 4 equations and 9 unknown variables. So mathematically this equation is underdetermined and is thus impossible to solve. Okay, so that's why what we do is we try to resolve or obtain the stress tensor in terms of the velocity components. And if you remember, we represented it in terms of the velocity gradients, okay, which we named as this strain rate tensor. Okay, there was again a strain rate tensor, if you remember. Okay, so now what you have is, now these stress components are indeed related directly to the velocity component, so the number of variables are now reduced. So since stress components are directly related to velocity, so we only have now 3 velocity components, and what's remaining is the pressure. So pressure is still needs to be determined, so it is treated independently from the velocity field. Okay, so now you have one pressure, which is a scalar field, and 3 velocity components. So we have total of 4 variables, and again we have 4 equations, that is the 3 momentum equations along the x, y and z direction, of course depending on the coordinate system that you choose. But for 3D velocity field you will have 3 independent equations, yeah, along the x, y and z direction, and one continuity equation. So in total you have 4 equations and 4 variables. Now the system is consistent, okay, and is possible to solve. I'm not saying we can solve it, but I'm saying it's possible to solve. But now again the problem is that even if it is possible to solve mathematically, you can claim that the equation is possible to solve, but still till now the Navier-Stokes equation for a 3D velocity field is not solved. Okay, it has remained unsolved, and is indeed one of the problems set up by the Clay Mathematical Institute, and is named as the one of the millennium problems. Okay, so if you look into it or Google it, you will understand about the 7 millennium problems that are unsolved in the field of physics and mathematics, and Navier-Stokes equation is one of them. Okay, although we can claim it to be solvable, but it is still unsolved. Okay, because of the complexity that arises because of the presence of the non-linearity in the equation, highly non-linear terms in the equation. But interestingly, the Navier-Stokes equation is indeed not a fully non-linear equation, but is actually a quasi-linear equation. Okay, I think I am moving a bit away from the discussions that are under the scope of this given course, but just wanted to tell you about this equation a bit more, that this equation is still unsolved and is almost impossible to solve. Okay, but again the price is very very high, that if you're able to solve this equation for a 3D velocity field, you get $1 million from the Clay Mathematical Institute and the Nobel Prize. Okay, so that's your motivation for your career ahead, I guess. But again, you should be careful to dive deep into understanding or solving these equations. Okay, of course I'm talking about the analytical equations. Numerically you can solve it, and that's how you are able to obtain the beautiful CFD plots of the pressure and velocity field, say past a airfoil or airplane or supersonic jets. You're able to do it because you're solving numerically but not analytically. Okay, so that's the catch. Okay, so now just again taking one example, if you consider I is equal to 1 and u1 equal to u, considering just I to be along the x direction, so you can just going back simplify this equation in as such. Okay, so you have dou by dou t of rho u plus dou by dou x of rho u plus dou by dou y of rho u v plus dou by dou z of rho u w is equal to dou by dou x of tau xx, dou by dou y of tau xy, dou by dou z of tau xz plus rho bx. Okay, so by applying the constitutive relationship, I will again let you know what is constitutive relation. You can obtain the relation between this shear stress and the velocity gradients, and then replace this shear stress in terms of the velocity gradients, and then simplify this equation even further, and that's how you get the Navier-Stokes equation. Okay, again imposing the condition of the fluid being Newtonian and the Stokes hypothesis. Okay, so again let us not go ahead of ourselves, let us go step by step, but this is how what we do. And you can see that even in its current form, this equation seems quite notorious and very difficult to be solved. So you know the complications that arises while discussing or trying to solve a Navier-Stokes equation. Okay, so, and again, just one more point, this shear stress components, okay, these stress components or stress tensor components can be decomposed into two parts. Okay, first is the hydrostatic component and the deviatoric component. Okay, so the hydrostatic components are basically normal stresses and the pressure. Okay, so these are normal stresses which includes the pressure, and the deviatory component are basically stress components that arises because of the relative motion of the fluid layers. Okay, so if there is a relative motion between the fluid layers, this will be your total stress tensor. Okay, and if the fluid is at rest or under rigid motion, the deviatoric stress component will be equal to 0. That's what it means. Okay, deviatoric, the deviatoric term basically means that stress components deviating from the hydrostatic part. Okay, that's why the term deviatoric. I think it is a way for you to remember. Okay, now we know that the hydrostatic stress components can be represented in terms of the pressure. Okay, in terms of pressure, the critical part is how to model the deviatoric stress components. Okay, so that's where we apply the constitutive relation. Okay, so constitutive relation is basically the relation between the stress tensor, or specifically speaking the deviatoric stress tensor, and the rate of deformation. And you know, but by rate of deformation I mean the velocity gradients. Okay, so for Newtonian fluid, that's the first assumption that we impose, that we consider the fluid to be Newtonian. Okay, and if we consider that, what happens is that this constitutive relation between the stress and the rate of deformation becomes linear. Okay, by applying the Newton's law of viscosity. Okay, so tau ij can be mapped with the deformation tensor, that is the strain rate tensor, by using a fourth order tensor. Okay, if you remember, even in today's class only, we mapped a vector to another vector. That is the tensor, sorry, the what was that, I'm just blanking out. Let me just go back. Just blanking out for this. Traction vector and the normal. We mapped the traction vector over the normal vector using a second order tensor, that was the shear stress tensor. Okay. So similarly, now since our tau ij and EKL, that is the shear stress tensor and the velocity gradient tensor, are both two second order tensors, to map them we use a fourth order tensor. Okay, so in general, this fourth order tensor, thisCijkl, should have 81 independent components. Okay, but now I expect you not to get scared, but we impose some assumptions that simplifies this fourth order tensor dramatically, and we are able to find a form of this constitutive relation that can be handled well and can be analytically processed further. Okay, so that's what we do. So the first assumption is that we consider, since, not assumption, the implication is that since tau ij is symmetric as well as EKL is symmetric tensors, the 81 independent components in theCijkl tensor is reduced to 36 independent components. Okay, and now that is the most critical part, and something that I won't explicitly derive or discuss, which is primarily because is far beyond the scope of the present course, and indeed is a very advanced topic to discuss, and advanced mathematics involved to come to this conclusion. So I won't discuss about it, but I will give you the idea that, again, which was discussed in the class, that if you assume the scenario, if the flow is homogeneous and isotropic. Okay, homogeneous means position independence and isotropic means direction independence. If you consider these assumptions, okay, if you consider these two assumptions and impose them on the strain rate, on the mapping tensor, you can now simplify this relation in terms of writing this relation between the stress tensor and the strain rate tensor as such. Okay, so if tau ij is equal to tau ij hydrostatic plus tau ij deviatory, tau ij hydrostatic is basically the pressure term, okay, because of the hydrostatic law, and I will again come to this delta ij term, and this term, that is the mapping between the stress tensor and the strain rate tensor, is now simplified into this form. Okay, I think maybe if some of you are master students or PhD students, maybe you can look into it, why we are able to obtain this form. But again, for at least for the scope of this course, it is not necessary. Okay, but how you are able to obtain it, maybe I will encourage the students who are interested to look into it. Okay, so I think there are some new terms in in this equation that some students might find a bit unknown, that they might not know. Okay, so let me just look into it and let us discuss. So the first term that is clearly unknown to you, I guess by now, is the delta ij term. Okay, this term, delta ij. So what happens is that it's for a very simple, I would say in a very simple way, what I can say is that this delta ij is basically used to convert your scalar field to obtain your convert basically a scalar field into a second order tensor. Okay, I know this definition is quite wrong. Anybody who is very expert in this, looking into it, they might be very angry upon me. But my understanding is that in a very simplified case, it basically is generating a second order tensor using a scalar field, of course keeping intact the mathematical interpretation of these tensors correctly, but is able to generate a second order tensor. So basically, for P for you was just a scalar field initially, but what this delta ij term is doing to you is that it is not making you able to add this scalar field correctly into the second order tensors, so that the physical implications are also kept intact, but you are able to convert this scalar field into a second order tensor, that what basically makes the additive manipulations possible. Okay, so what happens is that this del ij has a property that if I equal to j, okay, if I is equal to j, then del ij would be equal to 1. So basically del 1 1, del 2 2, and del 3 3. So these terms would be equal to 1. But for all other terms, that is I not equal to j, del ij equal to 0. So you can clearly see now that because of this manipulation, of course these terms also there now. So because of this manipulation, these terms, okay, these two terms minus p and lambda e k k will have its contribution on the stress tensor only at the diagonal components or the normal stress components. Okay, because for all other parts, this I not equal to j, both these terms are equal to 0. Okay, so only term that remains in those non-diagonal elements of the stress tensor are these terms. Okay, I hope it is clear. Okay, I think I might have, I don't know, I tried to make it simpler, but I hope it was understandable. Okay, if there's any doubt, you might ask, and if there's any further doubt, you can of course put in a discussion forum. Okay, we'll also have an additional session in this course after the final week. We'll have an additional session. You can treat that as a doubt clarification session as well. I will just briefly go through the entire course, touching upon the important concepts once again, and that in that session you can discuss any doubt related to the course very freely. Okay, there is no chronology required, so you can maybe take the help of that session if there's any doubt. Okay, so this is the final form of your strain rate tensor. I'm sorry, the stress tensor in terms of the velocity components. Okay, So you might say the pressure is there because we are not modeling the hydrostatic part, but the deviatoric part is now modeled in terms of the strain rate tensor, that is the velocity gradients. Okay, so both these terms have velocity gradients, and we are able to obtain the relation between the deviatoric stress components and the velocity tensor. Okay, velocity is, I'm not velocity, is a strain rate tensor, okay, which is basically velocity gradients. Okay, so I will wait for some time. So if there's any doubt, you may, if there's any doubt, you can ask. Okay, I'll wait for say 2 minutes. I'll wait for 2 minutes, and if there's no doubt, we will proceed further. Okay. Okay. So if there's no doubt, I think we can proceed further. Okay. So I think now you understand the script of today's discussion. By now you understand what we are going to do next. Okay. I think it's quite obvious. It's very simple now. Just substitute this form of tau ij in the Navier's equation and then see what we get. Okay. But still one thing remains, and I think by now you know it. Okay. We can replace it, but now we are having two unknown terms. Okay. One is lambda and 2 mu. And mu, basically. Mu is the viscosity, which you already know by now, which is the, what I can say, is the integral part of the Navier's equation that you know by know. Like one way or another, we have discussed it previously also, or if you already read it somewhere in your textbooks or any part of the course that you have taken previously in your bachelor's, you already know that mu is there. The kinematic viscosity, or mu, this dynamic viscosity, is the integral part of the momentum conservation of the Navier-Stokes equation. But what about lambda? What is lambda indeed? So lambda is again popularly known as the second viscosity. Okay. So like from textbook that we have referred, and again indeed in this textbook is also known as second viscosity, but let us see how we handle it. Okay, so let us proceed further. So again we have the Navier's equation, or the Cauchy momentum equation in our hand, which is given by this form. Okay, so again I think just one thing to address. You might feel that I've written it while discussing the lectures. I've written all the notes previously and I'm just repeating it. So I apologize for that. Okay, but the thing is, for any students watching the lectures or attending the course, it is expected that they write their own notes by looking at the video lectures by Prof. Chakraborty. Okay, these sessions or problem solving sessions are inherently meant for understanding or revising the concepts first. Second is to solve some relevant problems that are important for your assignments and your exams. Okay, so those are the two main objectives for these sessions. Okay, but given the time frame, I feel that it's just good to just quickly go through the concepts that were discussed in the class, and that's why I just write my notes beforehand and try to discuss it among you, with you, expecting that some doubts might arise, like you already wrote your notes, and some doubts might arise while the discussion. Okay, so that's why I'm not writing it inherently like that, then that would become a lecture. Okay, writing it together along with discussing, that becomes a lecture. So this is more of like a doubt clarifying session. Okay, but given the time frame, we tend to discuss thoroughly everything that were discussed in the lectures, but the main idea still remains that it's basically a doubt clearing session. Okay, so please keep that in mind, and that's why I'm not just writing it along with all of you while discussing the concepts. Okay, that it's expected that you write the notes by watching the lectures, okay, by Prof. Chakraborty, and I think that's far more better than what I'm doing here now. Okay, his concepts and understanding is far more deeper and better than me, which inherently becomes like a bible for this fluid mechanics course. Okay, so it's just better to write your notes, understand from his discussions and not mine. It's okay, mine is more like a brief overview rather than in-depth understanding. Okay, so yeah, just wanted to clarify that. Let us proceed then. Okay, sorry for taking the additional time. Yeah, so now we know that we need to impose this stress relation in this term of the Neighbors equation or the Cauchy momentum equation, and then see what happens. Okay, so if you remember, of course this is the final form of the stress tensor that we have after applying the simplifications, that is the isotropic assumption, Newtonian fluid, and the homogeneous assumption. Okay, these are the assumptions that we made to obtain this from the equation. Okay, now you can see that this part basically represents the rate of angular deformation. Okay, and this part in the deviatoric stress component represents the rate of volumetric strain. Okay, and that arises only in the normal components of the stress tensor. Okay, so now you know that if the fluid is at rest, the stress tensor basically boils down to the hydrostatic stress tensor, or the pressure only depends on the pressure. Okay, basically what will happen is that I will just write it for your clarifications. For hydrostatic case, your concerned stress tensor will basically be this one. Negative sign, you already know why it is there, because it is an inward acting force. Pressure is always acting in the inward direction considering the normal vector to that area. Okay, you might point out an example like if there's a pressure vessel, then pressure tends to be acting outward, but that's not the case, because even if it's a pressure vessel then pressure acting on the inner surface of the pressure vessel is again acting in the opposite direction to the normal vector for the inner surface of the vessel. Okay, in that case again it's generating a compressive action, although it in general it is causing the enlargement or the expansion of the pressure vessel, but to that particular region inside the pressure vessel where the pressure is acting, at that particular point it inherently acts as a compressive force. Okay, that's why the negative sign. I think, and to understand it better, you need to be able to visualize that idea, but it is consistent with that understanding. Okay, so now let us look at the just give me 1 second. Okay. So now let us, as I mentioned, we need to find how to discuss or how to remove, I won't say remove, but how to handle this second viscosity term in the Navier-Stokes equation. Okay, so what we will do is, from this equation, let us now consider only normal stress components. Okay, you will see why we are doing it. Okay, because there's a very good, nice relation between the normal stress components and the pressure. Okay, under certain circumstances, that's why we are doing it. So if you just take the normal components of this entire stress tensor, what you will, and like if you just take tau 11 plus tau 22 plus tau 33 and divide it by 3, what you will get is this. Okay, if you simplify it, I won't go to the steps. Okay, but if you just take only the normal stress components of this entire stress tensors, you will end up with this, something like this. You will end up something like this. Okay, see, this lambda term, basically lambda by del uk by del xk terms comes from this term. Okay, all other terms are 0 and we are not even considering it, we are only considering the normal stress components. And this term, like basically now becomes dou ui by dou xi plus dou ui by dou xi, so it becomes 2 mu dou ui by dou xi. Okay, and we divide it by 3, so it becomes 2 mu by 3, which is basically shown here. Okay, so we have tau 11 plus tau 22 plus tau 33 divided by 3 would be equal to minus p plus lambda by 2 by 3 mu times dou uk by dou xk, which is basically the divergence of the velocity field. Okay, just check it whether this is correct or not, and you can try it out. It's very simple. Only consider normal components of the strain tensor, of the stress tensor. Okay, so now we know that, we very clearly know that this tau 11 plus tau 22 plus tau 33 divided by 3 actually represents the mechanical pressure. Okay, so this is the mechanical pressure, minus this is equal to minus pm, and right hand side we have some pressure term which is basically thermodynamic pressure, minus p plus lambda by 2 by 3 mu plus dou uk by dou xk. Okay, so mechanical pressure, you know that is basically a translation, is the implication of a translation mode of energy of molecules. Okay, and the thermodynamic pressure is basically translation plus vibration plus rotational mode of energy of the energy molecules. And the Stokes hypothesis states that, from Stokes hypothesis, it turns out that the mechanical pressure is indeed actually equal to the thermodynamic pressure, and it would only happen when lambda plus 2 by 3 mu, this term is equal to 0. Okay, that is the first. Let me come, what are other scenarios when this case is valid. Okay, so this would happen irrespective of the type of the velocity field. If lambda plus 2 by 3 mu is equal to 0, then lambda will be equal to minus 2 by 3 mu, and the Stokes hypothesis would be valid. That is, mechanical pressure would be equal to thermodynamic pressure. Okay, I'm sorry. Now the case is that for monoatomic gases, okay, I think you already know what monoatomic gases mean, that exist in monoatomic form, such as helium and all the noble gases. In that case, the Stokes hypothesis is exactly valid. Okay, and it does not require any kind of other approximation, that is the velocity field to be incompressible or anything like that. It's not needed. Okay, but other than that, along with it, if the first incompressible, okay, if the first incompressible, then also a mechanical pressure becomes equal to the thermodynamic pressure. Okay, and thus the validity of the Stokes hypothesis is not required for this mechanical pressure to be equal to thermodynamic pressure. Okay, but see, once you impose Stokes hypothesis, see, considering the flow to be incompressible satisfies or results this mechanical pressure to be equal to thermodynamic pressure. But if you impose explicitly that the Stokes hypothesis is valid, then this lambda becomes equal to minus 2 by 3 mu. Okay, that's how this relation is obtained. Okay, so now what we do is we'll add one more assumption to our existing form of the Navier-Stokes equation. Okay, that now we will impose the Stokes hypothesis in our discussion. Okay, so now you understand what we basically do. It will replace the second viscosity lambda in terms of the dynamic viscosity mu. Okay, so let's see how the equations are modified now. Okay, and one more key takeaway is that since mu is always positive, the second viscosity always turns out to be negative. Okay, and as an exercise, I would let you discuss what lambda being negative has implication on the fluid flow. Okay, it's just a brief paragraph, small paragraph in the textbook. You might look into it, or even again take the help of Google or any other search engine. Okay, to understand it. Now substituting the value of tau ij in the Navier equation, you will get, or the Cauchy-Montaigne equation, you will get dou by dou t of rho ui plus dou by dou xj of rho ui uj is equal to dou by dou xj of minus, now just replace tau ij by this entire term. It is minus p delta ij plus lambda del uk by del xk delta ij plus mu dou ui by dou xj plus dou uj plus dou xi, dou uj by dou xi plus the body force term. Okay, now we'll just go term by term and see what happens. Okay, so we have this term, from this you will get minus dou p by dou xi. Okay, now if you operate on this term, you will get dou by dou xi of lambda dou uk by dou xk. Okay, how this happened, how the operation between the differential operator and the conical delta how this is obtained, that is the operation between the differential operator dou by dou xj and delta ij, that is conical delta, ends up as dou p by dou xi. It's something I think you can read in the textbooks by Prof Chakraborty. That's where they discuss about the tensor notation or tensor algebra. Basically, like if you have dou by dou xj times delta ij, if these terms exist, then just cancel these two. In a way, just cancel out these two indices, the repeating indices, and just consider the free index, that is xi. So you will have dou p by dou x. Similarly, dou by dou xj of this term again will have the independent index, that is dou by dou xi, times again this term that you have lambda times dou uk by dou xk. Final term is much more simpler. You just have dou by dou xj of mu dou u by dou xj plus dou by dou xj of mu dou uj by dou xi. Okay, and considering the velocity field to be smooth, you can simplify the other term, this term as mu times dou by dou xi times dou uj by dou xj. Okay, basically like you can just interchange the order of derivation, okay, or derivatives. Okay, then you can write dou uj by dou xj as something like dou uk by dou xk. Again, doesn't matter, you just change the indices. Once you do that, what you will see that the equation again can be again further processed as left hand side remains same, so I will not discuss it again. But right hand side, what happens is that you had dou p by dou xi, that is this term. Then you will see that there is a this term, the volumetric deformation, that is dou uk by dou xk term is there in both of these terms. So you can take this dou by dou xi common out of the as a common and just sum these two terms. Okay, so you will have lambda plus mu dou uk by dou xk. Okay, considering that lambda and mu are not functions of space. Okay, plus the final term, is dou by dou xj mu dou I by dou xj plus rho bi. Okay, now if we impose the Stokes hypothesis, because in this form of the equation you still have both lambda and mu, so what you need to do is you need to now impose the Stokes hypothesis. This lambda equal to minus 2 by 3 mu. So from that you will get these 2 minus 2 by 3 mu, to this entire term will become mu by 3. Okay, so by applying Stokes hypothesis, the final form of the equation that you get is rho times dou ui by dui by dt to be equal to minus dou pi by dou xi plus dou by dou xi of mu by 3 dou uk by dou xk plus dou by dou xj of mu dou ui by dou xj plus rho bi. Okay, and let me just go back. Okay, again you might ask how we obtain this term. Again, you just simplify these terms a bit. So this term becomes rho times dou u by dou xt plus ui times dou rho by dou t plus this term becomes ui times dou by dou xj of rho uj plus rho uj times dou ui by dou xj. Okay, so if you just take these two terms together, so you will have rho times dou ui by dou t plus rho uj plus dou ui by dou xj plus ui times dou rho by dou t plus dou by dou xj of rho uj. And if you know, this term is basically equal to 0 for mass conservation. Okay, so you are only left with this term, and this term is basically this complete derivative, that is rho times dou ui by dou t. Okay, I think it's quite well understood by now, so I don't think I need to discuss elaborately regarding this. Okay, so once you do that, this form the equation that you get is the Navier-Stokes equation for a generalized case. Okay, that we consider the fluid to be homogeneous and isotropic, the fluid to be Newtonian, and impose the Stokes hypothesis and considering a stationary reference frame. So once you do it, this is the final form of the Navier-Stokes equation. Okay, and the final part that you can do to simplify this equation even further and get back to the final form of the equation that you know, that everybody knows as the Navier-Stokes equation, is to consider a flow to be incompressible. Okay, so if you consider a flow to be incompressible, now you know that this term becomes equal to 0, dou uk by dou xk term equal to 0. This is basically delta dot v. This is equal to 0 for an incompressible flow. Then this form of the equation is reduced to this form. This rho times dui by dt to be equal to minus dou p by dou xi plus dou by dou xj of mu times dou ui by dou xj plus rho bi. Now if you consider mu to be, again it is already considered independent, so it becomes mu times dou square ui by dou xj square. Okay, which is basically this form, that is the mass celebrated from the Navier-Stokes equation that every one of us knows beforehand. Okay, so just to reiterate, these are the assumptions. For this equation, that is the flow has to be incompressible, Newtonian and Stokesian fluid, and the fluid has to be homogeneous and isotropic. Okay, so given that we went to each and every steps of the derivation in complete detail, so now you know where the assumptions were made and how it indeed modified or simplified the equation. Okay, so I think that there should not be any doubt by now. Okay, and I think for a problem solving session we had a very elaborate discussion on these equations, which I think is very, very important for any basic fluid mechanics course, and that's why I emphasized on giving this much time in this discussion. Okay, so I hope you understand it and understand the importance of these derivations. Okay, so in vector form, this equation can be written as rho times dou v by dou t plus v dot del v equal to minus del p plus mu nebula square v plus rho b. Okay, this is the Navier-Stokes equation, of course considering these assumptions in the vector form. Okay, so now I will take some time. I will take say 2 minutes just to, of course, give my throat a bit of rest. Again, that's also important since I've been speaking for the last 1 hour, so I think it's just understandable that I give my throat a bit of rest. Meanwhile, you can just look and appreciate the final form of the Navier-Stokes equation and just try to recollect from your notes that you might have taken in today's class or in the lectures, and try to correlate how we ended up in this form of the equation. Okay, because after that we will discuss the first exact solution, that is flow between two parallel plates. We discuss the exact solution, and after that we will directly solve some relevant problems for your assignments and your exam, and then we will call it a day. Okay, so with that, let me just take a bit of rest for 2 minutes, and then we'll resume our discussions. Okay. Okay, so I think now we can resume our discussion. So let us consider the first exact solution. Okay. The first exact solution that we consider is actually the flow between two parallel plates, or more specifically speaking, two infinitely large parallel plates. Okay. Why? Because the dimensions along the x direction and and the z direction is considered to be infinitely large. Okay, and any kind of interesting flow behavior that arises is actually along the y direction. Okay, let us again see how how we are claiming it. Okay, so this kind of flow is also known as the Hagen-Poiseuille flow. Okay, I think I should have written it, but just write it here. Oh, not Hagen-Poiseuille flow, I'm sorry, plain Poiseuille flow. Okay. So let us consider two infinitely large parallel plates. So basically this plate would be infinitely large along the x direction and along the z direction, that is along the depth of the paper. Now, so by this you can understand that if the flow is along, say, along the x direction, and if the plate is infinitely large along the z direction, say, okay, then what happens is that there is no interesting change in the behavior of the flow along the z direction. Okay, so after some time, after the initial, say, behavior of the flow, after initial developing region in the flow, it essentially attains a uniform velocity profile that is consistent along the z direction, and there is essentially no change in that direction. Okay, and along the x direction also it attains a constant form. Okay, basically this velocity profile does not change as we move further in the x direction. Okay, so after the flow is fully developed, again I will just come back here again, but just saying that after the flow is fully developed, dou u by dou x would be equal to 0. There is no change in the velocity profile along the x direction. Okay, so let us discuss about this developing region, so which will again exist in the case of pipe flow as well, but for the simplicity of the flow and for us being able to solve the flow exactly, we'll only consider the flow in the fully developed region. Okay, as the term itself discusses or implies. Okay, so once the flow occurs from the entrance of these two parallel plates, so there will be a generation of boundary layers. Okay, again I feel very bad that we will not be discussing thoroughly about boundary layers, which we should have been discussing, but for the scope of this course and for the time being, we will not discuss our boundary layer theory. But still, basically because of the presence of viscosity, the incoming flow will be slowed down by interacting with the walls of the plates, and then they will form a boundary layer. Both the upper plate and the bottom plate will generate a boundary layer, and they will develop for certain period and then converge at a point. Okay, converge at a certain point, and beyond that, after that, we say that the flow is fully developed. Okay, so the point beyond, up to which the point at which the two boundary layers have merged, we say that at up to that region we have the entrance region. Okay, from the starting of the plate up to the point where the boundary layers have completely merged, we tell that region as the developing region, and beyond that region we have a fully developed region. Okay, the region of our current interest. Okay, so you can see that even in the boundary layer, say even in the developing region or the entrance region also, you can say as that the velocity develop, we can approximately draw the velocity profile. Okay, let us see how it is drawn. Okay, so starting from the upper surface of the plate, velocity would be 0 at the upper surface of the plate because of no slip boundary condition, that tangential velocity component is equal to 0. So it will reach up to a certain value, not equal to infinity. Why? Because in this region at the core where the flow is essentially inviscid, or we assume to be inviscid, not because again viscosity is 0, but the velocity gradients are so small that they are not able to manifest this shear stress from the walls. Okay, that's why it will attain a certain value. Okay, say at this point, say at point A, and then it will remain uniform in this potential flow region or the inviscid region, and then again once it meets the boundary layer from the bottom plate, it will again velocity will again reduce and reach to 0 at the bottom plate. Okay, so you can see the structure. So you can see that the velocity profile increases up to a certain point till it reaches the boundary layer, which is 99% of the velocity at this region. Okay, not a free stream velocity, but at this region, and then it remains constant. Why? Because the flow is essentially inviscid, and again then attains this parabolic velocity profile. Okay, but since the flow is developing, you will see that in the later part of the developing region, you will see that the velocity indeed actually increases further. Okay, and you will see that the flow is increasing from the boundary layer, from the plate surface. Okay, surface of a plate to say up to the boundary layer, and then again attains a little bit of constant value because the region where the flow is essentially in viscous, and again then once the boundary layer starts from the bottom plate, again it reduces to 0 at the surface of the bottom plate. Okay. So why this happens is because since the wall effect is propagated further when the flow is developing, and that's why the velocity profile has to change to maintain the flow rate. Okay. So this is written here, and I think you can just take it for granted for now, because again, why the velocity profile changes as we move further into the plate again needs a bit more understanding of the boundary layer and the other concepts such as displacement thickness and those things. So for now you can just consider that the velocity actually changes or essentially increases as we move further into the developing region. Okay. So essentially you can say is that the velocity increases as we move from point A to point B. Okay, because of the effects of the wall and the inherent acceleration in the flow generated to maintain the same flow rate because of the effects of the boundary layer. Okay, so if there is any doubt, I think anyone who is listening to this particular point of discussion right now would essentially click like there has to be a bit more refined clarification for this. I understand that, but for now, since for the sake of saving time, I am skipping the discussion. The detailed discussion is given in a textbook and was discussed very thoroughly in the lectures. But for now, I am skipping it. But if there's, you can go back to the lectures to clarify that out, of course. But again, if you still feel unsatisfied, you can put that in a discussion forum or come back with that in the final session, the extra session, so that we can discuss it thoroughly. Okay, I will encourage that. But for now, I will just skip it. Okay. So the conclusion that we reach is that at point A and point B, at point B the velocity is higher because of the wall effects, a simple understanding. And that's why now we can, since this point A and point B, both point A and point B lies in the potential flow region or the inviscid region, we can essentially apply the Bernoulli's equation if you remember. Okay. So applying Bernoulli's equation in the inviscid region between A and B, so we'll have PA by rho plus UA square by 2 is equal to PB by rho plus UB square by 2. Okay. We are not considering gravity terms because they are on the same level. Then since UB is greater than UA, then for UB to be greater than UA, PA must be greater than PB. Basically, pressure at point B must be lower than pressure at point A for the flow to be accelerating along this direction. Okay. So this pressure being lower at the deeper end of the plane of the duct to encourage the accelerating of the flow or generate the flow is indeed known as the favorable pressure gradient. Okay. So if you take the, so in terms of derivative, so dou P by dou S would be equal to negative. Okay. Basically, like you can write something like PB minus PA divided by LB minus LA, and since PB is less than PA, it will be some minus P times LB, and LB is greater than LA, so it's something like L. In terms of differential, it is dou P by dou X, which is equal to negative. Okay, so it gives the negative pressure gradient indeed acts as a favorable pressure condition, okay, or favorable pressure gradient to actuate the flow or to encourage the flow in the positive x direction. Okay, I hope this is clear. Favorable pressure gradient. Okay. And now you can understand, and now you can understand, as long as this favorable pressure gradient exists, the flow will continue to occur because it will continue to, since the pressure is low, let me just write, since the pressure is low here, the flow will tend to flow in that direction and tend to maintain this particular flow, saying that the existence of this pressure gradient is indeed what that generates the flow or actuates the flow, and thus indeed for this kind of flow through ducts or pipes, the existence of pressure gradient or pressure gradient is indeed the driving force of the fluid motion. Okay. So let us consider a different case where if the plates are placed vertically, okay, then also this understanding is satisfied, okay, so we will have PA plus rho GHA by rho plus VA square by 2 plus PP plus rho GHB by rho plus VB square by 2. And you know that PA plus rho GHA basically represents the piezometric pressure, okay? And so in this case, you can write something like PA star by rho plus VA square by 2 is equal to PB square by rho plus VB square by 2, where PA star and PB star represents the piezometric pressure head or pressures, okay? Now, if VB is greater than VA, then we will have PA greater than PA star greater than PB star, representing again a favorable pressure gradient, okay? Which indeed in this case they are the piezometric pressure heads rather than the static pressure head, okay? So let us just now look into the assumptions that we take while deriving this exact solution. So again, while deriving these exact solutions, all the examiners tend to very much emphasize on the assumptions that were taken by the students while deriving the solution. Okay, why? Because these assumptions are not something like you write beforehand for making your answer longer or making your answer look like more knowledgeable. It's actually the fundamental conditions that you need to consider while deriving the solution. And without appreciating or considering these assumptions, you cannot really reach to the exact solution, okay? To reach the exact solution, there several assumptions had to be made, which is indeed very, very important and not just an ornamental part to your solution, okay? So don't skip the assumptions. Assumptions are not something that you write as an ornament, but it's something inherent or integral to your solution, okay? So that's why let us look into the assumptions. The first assumption is that the flow is steady, so any time the repetitive part in the equation will be equal to 0. You will see how the equation gets simplified because of these assumptions. Second assumption is that since the width of the plate, that's the width along the z direction, is much greater than the height or distance between the two parallel plates, so any gradient with respect to the z direction is equal to 0, okay? And since the fully developed region, the velocity profile does not change along the x direction, so we have dou u by dou x equal to 0, okay? This is the third assumption. Of course, considering the assumption of incompressible flow and constant density, that's already there while discussing the Navier-Stokes equation, but these are the new assumptions or explicit assumptions that you need to take by deriving the exact solution for the flow between two parallel plates, okay? Okay, so let us now proceed further, okay? So, okay, yeah. So for a steady 2D incompressible flow, we will have dou u by dou x plus dou v by dou y equal to 0, okay? We are not considering dou w by dou z because why? Again, dou w by dou z is 0 because dou y dou z of any term is equal to 0, okay? So for a fully developed flow, we have that dou u by dou x is equal to 0. That was one of the assumptions that we took. So we have dou v by dou y to be equal to 0, okay? That is first assumption, and we have v is not a function of y at all, okay? Now v is equal to 0 at y equal to h and y equal to minus h from the no penetration boundary condition, okay? And if that's the case, v has to be 0 for all y, because since v is 0 at both y equal to plus h and minus h, again I think I should revisit the geometry for this clarification, and v is not a function of y, so it essentially means that v does not change it y, and thus v is equal to 0 for all y, okay? So I will ask you to take some time to look into this consideration. At first it might seem for some people a bit indigestible at the beginning, but from the mathematical point of view, this turns out to be quite valid, and that's why v is equal to 0 for all the points in the flow field, and thus your flow field essentially becomes a 1D flow. That is, you have only one velocity component, that is along the u direction. It is in the x direction, that is the u velocity component, okay? So for clarification of geometry, what happens is that, I think you already saw, but just to clarify, we kept our coordinate at the center line of the velocity of the flow field in the flow between two parallel plates, and that's why this at the positive y direction, this becomes y equal to h, okay, and this becomes y equal to minus h, okay? So with that, let us proceed a bit further. So let's consider a generalized case. Again, for many textbooks, they just consider a simple case where the The two parallel plates are kept horizontally, but let us consider a case where it is kept at an angle theta. Okay. Let us see what happens, but you will eventually end up with the same equation. So we have, let us consider first the y momentum conservation equation. The trick is that you deal with the, like for example, if your flow is along the x direction, so deal with the flow along the x direction at the last, because you eventually see that the momentum equation from the other components, that is say along the z and y component, will give you some terms that you can conditions that you can impose on the x momentum equation to get the final form. Okay, again you can also go do the other way around, no problem at all, but it turns out to be a much cleaner way. Okay, let us see what we get. Okay, so for the y momentum equation, again mainly because since the v velocity component is equal to 0, that we got from this assumption. Okay, most of the terms on y momentum equation will be equal to 0. Some terms will remain, which we can then apply on the x momentum equation to get the solution. Okay, let us see what happens. So we have rho times dou v by dou t plus u dou v by dou x plus v dou v by dou y. I move very fast, I guess, but it's something that you already know, so I don't think I need to emphasize much upon that. Is equal to minus dou p by dou y plus mu dou square v by dou x square plus dou square v by dou y square plus rho by. Now from this diagram, if gravity always acts along the vertically downward direction, so we have g cos theta to be the body force along the y, minus g cos theta to be body force along the y direction, and g sin theta to be body force along, minus g sin theta to be body force along the x direction. Okay, yeah. So here rho by as minus g rho g cos theta. So we have, since it is steady flow, so this term will be equal to 0. Since v is 0, then all the terms including v will be equal to 0. Okay, so we're only left with the pressure gradient term and the body force term. Okay, so we have dou p by dou y to be equal to minus rho g cos theta. Okay, then if you integrate it, you will get pressure as minus rho g cos theta y plus some function of x. Okay, let us consider this as 1. Now the x component equation, this is the more interesting part. We have rho dou u by dou t plus u dou u by dou x plus v dou u by dou y to be equal to minus dou p by dou x plus mu dou square u by dou x square plus dou square by dou y square plus rho bx. Okay, so since the flow is steady, the dou u by dou t term equal to 0, not because u is 0, but dou by dou t of u is equal to 0 because the flow is steady. Now u dou u by dou x would have stood, because u is there, is non-zero, so this should have been there, and this would have been the first non-linear term that we had to deal with, which is again very notoriously difficult to handle analytically. Okay, numerically also we use some tricks to handle it, but we cannot again handle it very easily. Okay, there are some tricks used to handle this kind of non-linear terms while solving the equation, or quasi non-linear terms actually, to be more precise. But the thing is, this term would have been there if we wouldn't have considered the assumption that dou u by dou x equal to 0 because of a fully developed flow condition. So now you can see that because we inherently considered that the flow is fully developed, it essentially removed the non-linearity from the term, non-linearity from the equation that was there in the left hand side. Okay, in the convective acceleration terms. Okay, and that is the pattern that you will see. The assumption that we make, one way or another, removes the non-linearity that helps us to obtain the exact solution. Okay, we cannot obtain the exact solution if the non-linear terms exist, so we need to take the assumptions accordingly, of course, which makes physical sense, that helps us to remove these non-linearities from the equations. Okay, so considering the fully developed flow actually helped us in two ways. First was to remove this non-linearity, and second to make this flow essentially a 1D flow by making v equal to 0 for all the points in the flow field. Okay, so your left hand side is all 0, so now let's come to right hand side. So minus dou p by dou x will be there, of course it is non-zero. Dou square by dou x square is equal to 0. Why? Because dou u by dou x is equal to 0, so derivative of dou u by dou x also has to be 0. Now dou square u by dou y square is not 0 because u is not 0, so we don't know anything about dou u by dou y, so dou u by dou y is not equal to 0, and rho bx will be there, that is equal to minus rho g sin theta. Okay, so we have mu dou square u by dou y square to be equal to dou by dou x of p plus rho g sin theta x. Okay, where p, if you remember, is equal to some function of x plus minus rho g cos theta y. Okay, so from now, since dou by dou is equal to 0 and u is dou by dou z is equal to 0, because dou by dou z any term is equal to 0, so from that you can easily tell that u is only a function of y. Okay, so we have u as function of y only, so we can convert this as some function of some like mu times d square by dy square. Instead of having the partial derivative, you can have a complete derivative because u is function of y only. Okay, so we can write mu times d square by dy square to be equal to dp star by dx. Let us see how we simplify it. Okay, so if you look into this term, if you take the partial derivative, so since this function this term rho g by cos theta is function of y, considering rho g and theta to be constant, so this function of y, so dou by dou x of this term would be equal to 0, so we'll have dou by dou x of rho g sin theta x, that will be equal to rho g sin theta plus some function of x, that is f of x, say f dash x. Okay, so p star should essentially be rho g sin theta x, that is basically h. If you go back here, so sin theta x sin theta will basically give you the vertical height h, so we have rho g h plus some function of x, is fx. Okay, since now this rho g sin theta x or rho g h plus f of x is only a function of x, so we can convert this partial derivative to a complete derivative to dp star by dx, where p star is rho g sin theta x or rho g h plus some function of x, which is essentially the piezometric pressure head. Okay, or piezometric pressure. I should say not pressure head, it's pressure. Okay, not in terms of head. So now you see that the left hand side of the equation is function of y only and the right hand side is function of x only. Okay, so this scenario can only occur if both the sides are equal to some constant, say c. Okay, this again is a standard consideration while treating or while solving differential equations using separation of variables. So I think you can look into it if you want, but again it basically makes sense. Okay, it's very, very simple to imply that, so I don't think there's much more clarification required. Your right hand side is function of x only and left hand side is a function of y only, so this cannot be equal to each other if they are not equal to some constant c. Okay, so let us name this equation as equation A. So let us first solve the left hand side. Okay, so basically implicitly consider this dp star by dx to be equal to some constant c. Okay, so we have the mu times the d square u by dy square to be equal to c. If you integrate it with respect to y, you will have mu du by dy to be equal to c times y plus some arbitrary constant c1. Okay, now let us apply the boundary condition at y equal to 0. At y equal to 0, to have a finite velocity field, you will have dou u by dou y to be equal to 0, which gives c1 to be equal to 0. Okay, but essentially even if you go back in this case, the velocity profile that you get is essentially symmetric and finite. So dou u by dou y at this point has to be equal to 0 to maintain this symmetry, and that's why not dou u by dou y, du by dy actually. So you have at y equal to 0, du by dy has to be equal to 0, so we have c1 as 0, so we'll have only these terms left. Okay, so if we integrate it further, you will have, or integrate it again with respect to y, you will have mu times u to be equal to cy square by 2 plus some arbitrary constant c2. Now if we apply the boundary condition at y equal to h, we will have at y equal to h, u is equal to 0, so we'll have c2 to be equal to minus c square, because u is equal to 0, you take this in the left hand side, so you'll have c2 as minus ch square. Okay, and if you substitute this value of c2 in this equation, so you will get mu u to be equal to cy square by 2 minus ch square by 2, or u to be equal to c by 2 mu plus y square minus capital H square. Okay, now the critical part. Now let us consider that our flow is along the positive x direction. Okay, so u is along the positive x direction. Okay, so in that case it implies that u has to be positive for the flow to occur in a positive x direction. Okay, so we take u as positive. Now y square minus h square, if you go back to the geometry, this term, except the scenario where y is equal to h, is always negative, right? Because y cannot be greater than h within the given domain. Okay, let us come back here again. Like y cannot be greater than h. If this is our domain of consideration, then y cannot be greater than h. At max, it can be equal to h. So for the rest of the points in the flow field, if you disregard the boundary points, y is always less than equal to h. Okay, and y square minus h square indeed has to be always less than y square minus h square indeed always has to be less than 0, which means that y square minus h square is negative. Okay, but the thing is, your left hand side is positive and your right hand side is negative. Now for your left hand side to be positive, this term c by 2 mu has to be negative. So we told that c is equal to dp star by dx, if you remember from equation A. So you can write u is equal to 1 by 2 mu dp star by dx to be equal to y square minus h square. Now 2 mu is always a positive constant, so it means that for a flow to occur in the positive x direction, given this condition, this dp star by dx, which is actually a constant, should always be a negative, okay? So it basically tells us that for a flow to occur in a positive x direction, the pressure gradient always has to be negative, okay, which basically gives us the condition of the favorable pressure gradient. Okay, the existence of a negative pressure gradient along the x direction is indeed the favorable pressure gradient that generates the flow along the positive x direction. Okay, that's the key takeaway. Again, it's very difficult to understand it completely in the first go, but I request that you maybe go through the derivations, read the textbooks thoroughly, and then you will get a hold of it. Okay, then there are some interesting terms that are relevant to your problems. That is, first is average velocity, that is u bar to be equal to the integral of u dA divided by total area. Okay, so we'll have integration from minus h to h, because velocity variation is along the y direction, times u dy dot w. Okay, and area is again 2hw, again something that you can do it yourself. It's very simple to understand how we obtained it, so I will not go through the derivations. Go through this part, how we reached here. I will not go through it. Now if you substitute the value of u, the velocity profile that is obtained here, in this equation, you will get something like c mu by y square minus a square dy divided by 2h, integration from 0 to h. Considering that the flow field is symmetric, for velocity profile symmetry, you can just replace this integration from minus h to h as integration of 0 to h times 2. Okay, simple idea of an even function. Okay, how an integration of even function can be done. Okay, and again this is an even function, so we can understand why we did it. If you carry forward the integration, you will get u bar as c h square by 3 mu, or c bar, c, the constant c, to be equal in terms of the average velocity to be minus 3 mu u bar by h square, where c is basically the pressure gradient. Okay, you can see that all these terms, u bar has to be some constant value, h is constant, mu is constant. So basically it tells us that the pressure gradient in the case of fully developed flow between two parallel plates is indeed a constant. Okay, or if you represent the value of c in this equation, you can write u by u bar to be equal to 3 by 2 times 1 minus y square by h square. Okay, this is the parabolic velocity profile generated in the case of a fully developed flow between two parallel plates. Okay, now you can see that where u bar is the average velocity. Now you can see that for the flow velocity u to be maximum, can you tell me where the velocity will be maximum in the case of flow between two parallel plates? I think it's quite simple. It would be the region which is farthest away from both the plates, and that should essentially occur at the middle of the domain. So basically at y equal to 0, the velocity field will be maximum. Again, something that you can try to understand from basic mathematics or even from basic intuitive understanding. Okay, so at y equal to 0, u will be equal to u max. So we'll have u max by u bar to be equal to 3 by 2, because y equal to 0, this becomes equal to 1. So this will be equal to 3 by 2, or u max will be 3 by 2 times the average velocity u bar, which is one of the very fundamental results in the case of flow between two parallel plates. This question I think might come in your exams or even competitive exams such as GATE, like relation between the average velocity and the maximum velocity in the case of flow between two parallel plates. Okay, a standard result, but sometimes we might confuse it with the flow between pipes, which has again a different relation. Okay, so the next is the wall shear stress. So we find the wall shear stress by finding the value of the shear stress at the wall at y equal to h. So we have mu times du by dy at y equal to h. Why? Because v is equal to 0, and dou u by dy can be represented as du by dy because u is only a function of y at y equal to h. That gives us the wall shear stress at the wall. So we have mu times cy by mu. If you just carry forward the differentiation, so you will have this would be equal to 3 mu u bar by h. Okay, minus 3 mu u bar by h. That gives us the shear stress at the wall. Okay, this I think it's quite simple. Just take velocity field is given by this equation, right? 3 u would be 3 u bar by 2 1 minus y square by a square. Then du by dy would simply be minus 3u y by 2h square. Okay, if you not 2 would be cancelled out, so by h square. If you substitute the value of y as h, so you will have du by dy at y equal to h. You will have minus 3u bar by h. Okay, or tau wall would be mu times du by dy at h would be minus 3 mu u bar by h. Okay, quite simple to understand, so I think we can proceed further. Okay, so the final part is this, that is the friction coefficient, which is basically the ratio between the shear stress at the wall divided by the kinetic energy. Okay, so we have tau wall is equal to minus 3 mu, or you can take, let's say, if y equal to minus h, you can get a positive value. Just for simplification, we'll have 3 mu u bar by h, and kinetic energy is half rho u average square. In terms of the average velocity field, that makes much more clear sense. Okay, so we'll have, if you just simplify these expressions or these equations, you'll have Cf, the friction coefficient, or the fanning friction coefficient, which is also known as the fanning friction coefficient, as 6 by rho u bar h by mu. Okay, just simple manipulation of the equations. And now this, if you just replace h, if you multiply 2 with the numerator and denominator, you will have the numerator will have 12, and you will have rho u 2h by mu, where 2h gives us the characteristic length scale, and you know that rho times velocity times the characteristic length scale divided by viscosity gives us the Reynolds number in terms of the channel height. So we'll have Cf to be equal to 12 by REH. Okay, so yeah, that will be all for today's discussion part. So now let us take some examples. Okay, again, so since there are very few students in today's class, so what I would do is, again, just go through the answer quickly, and then if there's any doubt, you might ask in a discussion forum, because there are very few students today. I think the way that I'm going to handle it would be beneficial for all of us. Okay, so just to reiterate, I will just say it once, I guess, not repeat it for every question. So what you can do is, I will read the question, clarify the question properly. After that, if you want to solve it by your own, you can pause the video, since you will be watching the recording. So you can pause the video, try to solve the answer, get your answer, and then compare your solution with my answer that I will eventually say. Okay, so this will be that will be the agenda. So let me just quickly go through the answers for the sake of saving time and for a better or what to say, a fluid conducting this session in a very fluid manner. Okay, in a very smooth manner. Because of fluid mechanics, I'm using fluid everywhere. Actually, I just want to say in a very smooth manner. Okay. So the question is, a sealed journal bearing a sealed journal bearing is formed from concentric cylinders. The inner and the outer area are 25 and 26 millimeter respectively, and the journal length inner and outer area are 25 and 26 millimeter respectively, and the journal length is 100 millimeter, which turns at 2800 rpm. Okay, the gap is filled with oil in laminar motion. Okay, it's very important. The velocity profile is linear across the gap. Again, very important assumption. And the torque needed to turn a journal is 0.2 Newton meter. Calculate the viscosity of the oil. Okay, it's a very standard problem in the case of flow between two concentric cylinders. Okay, but the key thing here is that they have in reality, if the gap is not that small and if we do not impose the very thin gap limit, we cannot actually consider the velocity profile to very linearly between the two rotating cylinders. Actually, we are not dealing with it, but this is also not Taylor-Coit flow, so we are not doing it. I don't think we'll discuss the solution of Taylor-Coit flow in today's in this course, but which is again one of the exact solutions we can obtain for Taylor-Coit flow. So you can maybe look into it in the textbook. I think it is there, or you can again refer other textbook for Taylor-Coit flow discussions. Okay, so this is standard problem for Taylor-Coit type of flows, but here what they have done is that they have simplified the problem, considering the gap between the two parallel plates to be very small, and impose the linear velocity profile conditions. Okay, so let us see how it is solved. Okay, the consideration of the velocity profile to be linear simplifies the problem like very much. Okay, let us see what we can do. So we have since the velocity profile is linear, okay, so we have use as something like Vy by h. So this is basically the geometry. We have a inner cylinder rotating, which has a radius of r, and outer cylinder is stationary, which is rho. So velocity at the outer cylinder would be equal to 0 because of the no-slip boundary condition. And since the inner cylinder is rotating, so the fluid attached with the surface of the rotating cylinder, of course, will have 0 velocity, but relative to the stationary cylinder, the fluid will have a certain velocity, which will indeed generate the velocity profile. But this velocity profile is asked to be considered as linear because the gap between the two cylinders is very small. It's only 0.5 millimeter, right? So let us see what happens. So we have u is considered to be linear, so we have u as Vy by h. Now tau would be mu times dou u by dou y, or tau would be mu v by h. Okay, something like this. So mu times the velocity divided by the gap. Okay, so we will have tau as mu times u by r naught minus ri. Okay, which is the gap between the two cylinders. Okay, now u is actually the angular velocity times the radius. Since the inner cylinder is rotating, so the angular velocity would be omega times ri, but omega is obtained by knowing the rpm. Okay, so we have the shear stress as force, the shear force per unit area, F is the shear force, and area of consideration is the lateral surface area of the journal bearing, which is a cylindrical shape. So a lateral surface area of the cylinder would be 2 pi RIL. Okay, we are just considering the inner cylinder for simplification, so we just consider stress on the inner cylinder, because we know the velocity is dependent on the radius of the inner cylinder. So let us just consider the stress on the inner cylinder, and then we can discuss about torque and everything. Okay, and of course torque is also dependent on the inner cylinder's rotation. That's why we are considering the surface of the inner cylinder. Okay, now the torque is indeed the shear force times the radius. Okay, in this case, since the inner cylinder is rotating, the axis distance between the rotation and the axis of rotation is ri. Okay, application of force and the axis of rotation is Ri, this is the application of force, the shear force Fs, and the axis of rotation is Ri. Okay, just one, I repeated it many times, but I just wanted to actually clarify it or properly state it. So we have Ts Fs times Ri, or Fs, the shear force, is P by Ri. Okay. Now if you substitute the value of Fs in this equation, so we'll have tau to be equal to T by 2 pi r I square times L. Okay. So now from this equation and this equation we get the expression for tau, where we can just replace the value of tau from here to this. So we'll have mu times Ri omega divided by r naught minus Ri to be equal to T by 2 pi Ri square times L. Okay. Now to find the value of viscosity, just take this term in the right hand side of the equation and just substitute the value of omega, Ri, Ro, T and L. Then you will get the final answer, where you need to be careful that omega is in terms of RPM. You need to actually convert it in terms of rounds per second. So just do that carefully. Okay. So from that we will have mu as 0.00694 Pascal second. Okay, so that's how you obtain it. So answer would be option A. Okay. So let us look at the next question. Consider a steady, fully developed laminar flow of Newtonian fluid through a duct of radius r. Okay. At what local radius the axial velocity is equal to the average velocity? Okay. So at what point u is equal to u average? Okay. So again, it's very simple. You need to substitute the value of the velocity profile of u in this equation. So from that, what you will get. So we know that the velocity profile for a flow between through pipe is given by u is equal to minus r square 4 mu dp by dx times 1 minus r square by r square. Okay, again, this is something that we'll eventually discuss. Okay, the flow through pipe. Okay, but this is how we get the velocity profile. So this is actually the velocity profile. Okay, so something that you can maybe take it for what I say now, because we will eventually discuss about this. But for this current problem, let us just consider that this is the velocity profile of flow through pipe. Okay, we see that average velocity for flow through pipe is given by r square by 8 mu times dp by dx. Okay, so now to find the value of r at which the value of the axial velocity is equal to the average velocity, just equate these two terms. Okay, these two equations, this and this. So from that you can see that this is just the half of this one. So we'll have, if we equate these two terms, I think I should just write it. So you'll have minus r square by 4 mu dp by dx times 1 minus r square by capital R square to be equal to minus r square by 8 mu dp by dx. So you can see that dp by dx is cancelled, this again is cancelled, so we'll have a factor of half. So that's why you get half is equal to 1 minus r square by r square, or you will have r square by r square as half, or you'll get r as r divided by square root of 2. Okay, so the correct answer would be option B. Okay. So next question is, a class of very small Reynolds number flows known as the creeping flows occurs when the viscous force dominate over the inertia forces. Okay, which of the following might be the good approximation for a Navier-Stokes equation in a creeping flow? Okay, again a very standard question for competitive exams, and in this case you just need to use a basic logic. Okay, so actually this is the think what I will do is maybe just add one more term to make it complete. It is mu del square v. Okay, so what happens is that for creeping flows, the Reynolds number is very small. Okay, in that cases the viscous forces dominate over all types of force. Okay, so viscous force dominate over inertia forces. So that happens is that the order of magnitude of this term A, say this A, this is B, this is C. Okay, so the order of magnitude of A would be much greater than order of magnitude of B and order of magnitude of C. Okay, so that's why the only two terms that will be left in this kind of flows are the pressure gradient term and the viscous terms. Okay, so we'll have minus del P plus mu del square V to be equal to 0, or you will have del P to be equal to mu del square V. Okay, so correct option is option number B. Okay, so let us look in the question, next question. Okay, question number 4. A soda straw is 20 soda straw cylindrical system is 20 centimeter long and 2 millimeter in diameter. It delivers a cold ring approximated at 10 water at 10 degrees Celsius with density as 1000 kg per meter cube and mu as 1.3 10 to the minus 3 kg per meter second at the rate of 3 centimeter cube per second. What is the head loss through the straw? Okay, so again, just to help you out, I think again I don't make the questions, I just like discuss the questions that are already given to us. So what happens is that these questions are again relevant to something that we'll discuss in the next class, but just for a reference, again concepts are exactly the same. So again these questions make sense and maybe even acts as a motivation for you to understand the pipe flows. Okay, so just to give you a hint, which I think should have been in the question, the head loss in this kind of flow through pipes are actually given by this equation, that is HF is equal to mu L times Q is the volume flow rate divided by pi rho G d to the power of 4. Okay, so now you can see that the only thing that remains is that first is to clarify whether the flow is laminar or not. Again, since the area is given and the volt flow rate is given, you can easily find the Reynolds number. First find the Reynolds number, and this is valid for laminar flows. Okay, just to be clear. Okay, so if that's the case, then you can find the head loss that is being asked here through this equation. So again, what you do is first find the whether flow is laminar or not, and if it is laminar, then you substitute the value of mu, which is given. L is again given, that is 20 centimeter. Q is given as 3 centimeter cube per second. Pi you already know, rho and G you know, and D also you know. So just substitute the value of all these parameters in this equation, you will get the value of HF. So if once you do it, you find that first is to find whether flow is laminar or not. So we have RE as rho U average D by mu. Now U average is actually Q by pi D square by 4. Okay, so if you do it, you will find that the average velocity, the Reynolds number turns out to be 1460, which is Reynolds number is 1460, which comes under okay. So you see that Reynolds number equal to 140 comes under the laminar flow regime. So now we can apply the formula of head loss to obtain the head loss through the straw. Okay, so from that, if you just substitute the value of Q, L, D and of course rho, g and mu already, and mu of course. From that the head loss turns out to be 0.204 meter. Okay. So correct answer would be option B. Okay. So let us look into question number 5. So the question is, the velocity profile for a fully developed laminar flow through a pipe of length is given, pipe of length L, say length L is given as u equal to u naught times dp by dx times 1 minus 3 by 5 r square by small r square. Okay, where r is the radius of the pipe and r is the distance from the center line. For a fluid of viscosity mu, find the pressure drop per unit length of the pipe. Okay. So one thing that, of course, at the beginning the question seems a bit complicated because you don't know how to find the pressure drop per unit length. But the thing is, in the case of flow through pipes or in the parallel flow, flow between two parallel plates, this pressure gradient actually turns out to be linear. Okay, so dp by dx turns out to be linear. So basically, dp by dx is always equal to something like p2 minus p1 by, say, the length between these 2 points. Okay, because it is linear, because the dp by dx is constant, so it will give us the pressure variation to be linear. Now the key to this question is that you can see that all the terms in the options have an expression of average velocity. Okay, so you get a hint that you need to express your pressure drop in terms of the average velocity. You know the velocity profile. I think the task is quite simple to find the average velocity for a flow through pipes. Okay, the challenging part that I think here is that, again, the fact that we have not discussed explicitly about the flow through pipes, which we'll eventually discuss in the next session. But nevertheless, let me just give you an idea. Okay, we have the velocity profile as u is equal to u naught by dp by dx times 1 minus 3 by 5 r square by r square, which is the parabolic velocity profile. Now for flow through pipes, the average velocity is found out using this expression. Okay, let me give you an idea where u bar is again integration of u dA by total area. Now the elemental area that you need to take in terms of flow through pipes is actually 2 pi r dr. So which, if you know, if you have dealt with integration along the cylindrical surfaces or across cylindrical surfaces, so you will know that this 2 pi r dr is basically the area of the elemental ring that you consider. Okay, like for example, if you do the integration for along this circular surface, which would be the cross section of a cylindrical pipe, then the elemental area that you consider, say this is equal to r, then this would be 2 pi r and this width would be dr, right? Then the elemental area would indeed be given by, say, dA would be given by 2 pi r dr. Okay, the length times the width. Okay, this is how you get the elemental area, and area is again pi r square. Total area is pi r square, the cross sectional area. Once you do it, you will end up with this expression to find the average velocity. Okay, so now the task is very simple. Just substitute the value of ur. Okay, that is this in this expression and carry forward the integration. Okay, integration I think is a bit more, not complicated, a bit lengthy for this current case, so which I will skip for now. So you will have the average velocity as 7 by 20 times u naught dp by dx by r square. Since you have the expression of average velocity, just substitute all the, or take all the terms in the right hand side. So you have dp by dx would be equal to p2 minus p1 by l to be equal to 20 times u average by 7 u naught by r square. So the correct option would be option A. Okay. So I think that's all for today from my side. The next question also I think is for flow through pipes. I think I will carry forward this question in the next session as well, because I think unfortunately many questions for the today's class were regarding flow through pipes, which ideally should have been for the next session, but I think it gives a very good motivation and understanding, I must say, idea of how or what we will be dealing with in the next class. So I think in one way or another that turned out to be useful for us only. We should that take that as a uh, motivation to come to the next class and see how these problems will be solved. So yeah, so that's all from my end today, and there were very few students, so I think it would have been better if more students would have been in today's class, and I would have expected this session to be interactive, because I find today's class to be one of the most interesting classes to take, because it, what to say, introduces you to the Navier-Stokes equation, which will eventually end up as the fundamental equation for any one of you who is gonna have a career or a research career in fluid mechanics. So in one way or another end up in discussing Navier-Stokes equation. So I felt it would have been better if there would have been many students, but it's fine. I hope anybody who watches the recording ends up getting much more idea of what they are dealing with, and end up appreciating the course as well as today's discussion. Okay, so with that, thank you, and let's all meet next week.